Hello everyone. Welcome to 15-minute Hikkha platform. My name is Dr. Abhijit Hazarika and I work as a scientist at CSIR Indian Institute of Chemical Technology, Hyderabad. So the idea of this platform is to help our students, particularly the graduate and the undergraduate students, to understand the basic concepts and to broaden their knowledge on different topics in their syllabus. So today's topic is about fluorescence. I'll be talking about what fluorescence is, how it works in the fundamental level, and what are the typical applications related to this phenomenon. We all love glowing colors, right? And fluorescence is all about glowing colors. In scientific language, this is termed as color emission or luminescence. Now let me first give you some common examples of different types of luminescence. You all must have done flame test in your higher secondary chemistry labs, right? The beautiful colors you see in the flame test of different salts are actually examples of a kind of luminescence from the metals in the salts. And we all use these CFL bulbs or LED bulbs or these small different colored LED lights in decoration purposes, right? So this is another kind of luminescence. And here is another example of a different type of luminescent material, which is known as glow in the dark paint. So you can see these paints in different parties or in our common highlighter pen or our currency notes like 100 rupees or 50 rupees notes. So if you put this under UV lamp, you can see the color glow. And in biological system, the firefly glow is very familiar to us, right? So this green glow from the firefly is because of chemical reaction, and this particular compound, luciferin, is responsible for this greenish glow. And in different marine species like jellyfish, you can see similar kind of glow in dark, which is again because of some chemical known as cylindrazine. Now you can do a small experiment and very simple experiment at your home. You can take a small pinch of turmeric powder and put it in some alcohol solution. And if you expose the solution in UV lamp, you can see a greenish yellowish glow from the solution. So which is because of this chemical curcumin that is present in the turmeric powder. Uh, Also, we can see this luminescence in different kind of minerals found in nature, like aragonite, which is calcium carbonate, or fluorite or fluorspar, which is calcium chloride. They glow under UV lamp with different colors. Now, can all these glows be termed as fluorescence? It appears that only these particular examples, the CFL bulbs, these glow in dark paints, the turmeric powder, or these minerals, the luminescence from these materials can be termed as fluorescence. Incidentally, the term fluorescence was coined by Sir George Gabriel Stokes back in 1852 from this mineral fluorspar, calcium chloride. Now, what is common in all these examples? The common thing in all these examples is that they glow when some kind of light falls upon them. In 1852, Sir George Gabriel Stokes did a very simple experiment. What he did, he took a solution of quinine sulfate, this organic molecule, which can be found in anti-malarial drug or this commercially available tonic powders. And what he did, he took the sunlight and he dispersed it with the help of a prism. Then, when he put this quinine sulfate solution and slowly moved this solution from red to the blue part of the spectrum, what he observed, when the solution is put in the blue part of the spectrum, it suddenly turns cyan glow. So when I say that the common thing about all the fluorescence mechanism is that some kind of light is responsible for this phenomenon. So when I say some kind, it means that particular light with particular energy or wavelength. Now, since this fluorescence occurs because of light or photon, it is also called photoluminescence. In fact, fluorescence is a class of photoluminescence. There is another class of photoluminescence which is known as phosphorescence, which is nothing but delayed fluorescence. Now, let us look at what happens in fundamental level. So let us take a simple system where we have a ground level energy, electronic energy E naught and a higher level electronic energy E1, and there is the energy gap delta E. When light with energy which is equivalent to difference in energy between E1 and E0 falls upon the system, the electron at E0 jumps up to the higher energy level, that is E1. This process is called absorption or excitation. Now, immediately after the absorption, the excited electron comes back to the ground electronic state E0 and it emits some light with energy h nu. This is termed as emission of photon or fluorescence. Now, this happens in case of atomic system because the atoms have discrete energy levels. In the absorption and emission spectrum, you can see very discrete lines. So, in fact, this is very much similar to the flame test that you have done in your higher secondary chemistry laboratories. The only difference is that in your flame test, you are excited the atoms of the salts with heat, not with photon. Now from atomic system, let's go to a little bit complex system, which is diatomic molecule. So the electronic energy levels or the electronic states of the diatomic molecules can be represented by this kind of Morse potentials. Let's say we have a ground electronic state, which is E0, and then excited electronic state, which is E1. So when the molecule interacts with electromagnetic wave or light, they also vibrate. Because of this vibration, along with the electronic state, we will also have vibrational energy levels. So the electronic energy levels together with vibrational energy levels is termed as vibronic energy levels. And any transition that from one electronic state to another electronic state which couples with vibrational energy levels is termed as vibronic transition. Now, what happens when light falls on such system? So when light falls upon in this kind of system, the electron from the ground vibronic state goes from one of the vibrational level in the excited electronic state, that is E1, and because of this transition we get an absorption line. Now this electron trickles down quickly to the lowermost vibrational state within E1, and eventually this electron goes back to the ground electronic state by giving some fluorescence, and we can get a fluorescence line in the spectrum. So this electron now trickles down to the lowermost vibrational energy levels within E1. Now, as you can see, there are different vibrational energy levels, so there can be different transition depending on the extent of overlap of electron wave functions. So let's say we can have this transition, and if you combine all this transition, you will have a broad absorption spectrum. Similarly, in case of emission, you can have emission to different vibrational energy levels, and accordingly, if you combine all these transitions, you will have a broad emission spectrum. And the difference between the absorption maximum and the emission maximum is called Stokes shifts, after the name of this physicist Sir George Gabriel Stokes. Now, how do you know how much this system is fluorescing? So for this, there is a term called quantum yield is used. This is nothing but the number of photons emitted against the number of photons absorbed. So higher the quantum yield, higher the fluorescence capacity. Now, whenever we discuss about fluorescence, this particular diagram comes again and again. So this is called Jablonski diagram, against the name of Sir Alexander Zablosky. And this single diagram actually describes all the processes related to absorption and fluorescence. Now here in this picture, we have a ground electronic state S0, which is a singlet state. That means all the electrons have opposite spins. And we can have different excited electronic states like S1, S2, and so on. And all these blue lines are vibrational energy levels. Now, when the system absorbs light or electromagnetic radiation of sufficient energy, the system goes from S0 to one of the higher electronic states, let's say S2. And after the absorption, the system trickles down to the lowermost excited energy state, that is S1, by some processes called vibrational relaxation or internal conversion. And eventually the system comes back to the ground electronic state S0 by the process called fluorescence. These non-radiative processes like vibration relaxation and internal conversion, they are very fast as compared to fluorescence. So these processes takes place in the time frame of picosecond, while the fluorescence takes place in a time scale of nanosecond. And here on right side, here are the molecular uh, molecular orbital diagrams, and this fluorescence energy or the fluorescence color depends on the energy difference between the lowest unoccupied molecular orbital and the highest occupied molecular orbital. Now, when this transition takes place, the electron can also flip its spin, thus resulting a triplet state. Let's say we have a triplet state, triplet excited state T1, and while the system tries to come down to the ground electronic state, it may transit into T1 to the triplet excited state. And from the triplet excited state, the system eventually comes back to the ground electronic state S1. Now from the spin selection rule, this S to T transition or T to S transition is spin forbidden. So this is the reason why the phosphorescence process is very slow in the range of, let's say, microsecond to second. Now, as you have seen that the fluorescence color or the fluorescence energy depends on the energy difference between LUMO and HOMO. So let's take one example by which we can tune the fluorescence color. So here is an example. Let's say ethylene. So ethylene has the HOMO-LUMO energy gap which is around 6.7 eV or 185 nanometer. So we expect that the ethylene molecule will emit a light which is in the UV range, let's say 185 nanometer. So if we extend the conjugation and go to butadiene, then we immediately see that the HOMO-LUMO energy gap reduces. It's like 5.8 eV or 215 nanometer. So if you go further to octatetraene, the extent of conjugation is increasing, and accordingly the HOMO-LUMO energy gap is further decreasing. So this molecule octatetraene can emit in the visible range, which is around 400 nanometer. Now this is one example of a complex organic dye where we can see that the increase of extent of conjugation from molecule 1 to molecule 3 causes the fluorescence color from going from green to red. Now from atoms to molecules, let's go towards solids. In isolated atoms, we know that the energy levels are discrete, like we can have 1s, 2s, 2p, 3d, or so on energy levels. Now, when these atoms are arranged periodically in infinite three-dimensional space, so all the atomic orbitals from all the atoms come so close together that they form a continuous band. And like molecular systems where we have bonding orbital, non-bonding orbital, and antibody bonding orbital, in solids we have conduction band and the valence band. And depending on how the electrons are distributed within the valence band and conduction band, we can have insulator where the completely vacant conduction band and the completely filled valence band are separated by a huge energy gap, which is termed as band gap. If we look at metal, the conduction band and the valence band overlaps with each other. The conduction band is kind of partially filled. Now, in between, we have semiconductors. Semiconductors are very similar to insulator, but the energy gap or the band gap between conduction band and valence band is very small. And by applying small amount of energy, the electrons can be transferred from the valence band to the conduction band. For a discussion of our topic fluorescence, this material is very interesting. These are some examples of typical semiconductors like silicon, germanium, cadmium selenide, indium phosphide, etc., etc. Not only in terms of fluorescence, these semiconductors are very important in our daily life. If you look at computer, television, mobile phone, in all these applications, you have to have semiconductors. Now, like molecular system, if you put some light with sufficient energy on the semiconductors, you create a pair of electron and hole in the conduction band and the valence band respectively. And when this electron and hole recombine, they give the fluorescence color. We call this electron and hole pair as excitons. Now, if you can control the gap between the conduction band and the valence band, you can control the fluorescence color. Now let us go to one very unique system which is called quantum dots. They are nothing but semiconducting materials, but they have size range within 2 to 20 nanometer. So they are not atoms nor they are solids. Because of their small size, their atoms are arranged periodically not in infinite space but in finite space. And accordingly, their energy levels get discretized, very much like atoms. So that's why they are termed as artificial atoms. And these discrete energy levels are due to quantum confinement effect in these materials. And as you can see from this figure that if you control the size of the quantum dots of a particular material, you can control the band gap energy. Accordingly, you can control the fluorescence color or the absorption. So now let's quickly look at some applications related to fluorescence. They have many applications. So I'll only give you a couple of examples. So like in solid state displays and lighting, as I have mentioned earlier, they are used in CFL bulbs. So inside the CFL bulbs, green and red emitting phosphors or fluorophores are coated inside and they are excited with a mercury vapor which is generated by applying electrical energy. So this green and red emitting fluorophores together gives us the white color. The LEDs also have fluorescent materials inside them, but they work slightly in a different way. So in the LED bulbs, if you open up, you can see this kind of yellowish green color fluorophores, but they are excited by application of an electrical field. So this mechanism is called electroluminescence. And you can see electroluminescence in the colorful LED lights everywhere. So in terms of displays, if you look at televisions or your mobile phones nowadays, all of have LED displays, which is light emitting displays. So here in this television, in this mobiles, organic fluorophores are being used. That's why they are termed as OLED or organic light emitting displays. Nowadays, quantum dots are also used in displays. Now coming to biological applications, this fluorescent material have been used as biological marker or biological probe or biological levels. So in this particular example, a green emitting organic molecule or organic dye has been linked to a particular antibody. And this antibody is added to a specimen which is suspected to contain a particular pathogen. So now, if the pathogen is present in the specimen, and the antibody after linked to the specific antigen in the pathogen emits green color under fluorescent microscope. This way you will be able to tell whether this particular specimen contains the particular pathogen or not. So quantum dots are also nowadays used as biological markers, and the advantages of quantum dots are that the emission is narrow, stable, and they are less photoblessing as compared to organic dyes. So recently, the MIT scientists have used a specifically designed fluorophore to probe the electrical signal inside our brain. And in the medical technology, the fluorescent probes are used during surgery, which help the doctors to have better vision during complicated surgeries. Here is another example of how tumor cells can be imaged during a surgery. So all these biological imagings or fluorescent levelings can be possible because of this very unique and nice instrument which is called fluorescence microscope. So just before ending, it is worth mentioning about Nobel Prizes that are related to fluorescence. In 2014, the Nobel Prize in Chemistry was awarded for the development of super-resolved fluorescence microscopy, which helped in breaking the resolution limit of typical optical microscopes. Back in 2008, the Chemistry Nobel Prize was awarded for the discovery and development of green fluorescent proteins, which is also called GFP in jellyfish. So this has tremendously helped the researchers to develop ways to watch processes that were previously invisible. For example, development of nerve cells in the brain, or how cancer cells spread inside the cell. So in 2014 again, the Nobel Prize in Physics was awarded for the invention of blue light emitting diode. Gallium nitride based blue LEDs have brought tremendous revolution to our lighting application in an energy efficient way. So following these Nobel Prizes in 2014, the United Nations General Assembly in its 68th session proclaimed the year 2015 as the International Year of Light and Light-Based Technologies to raise the global awareness about how light-based technologies promote sustainable development and provide solutions to global challenges in energy, education, agriculture, and the health sector. So with this, let me thank you all for listening to this session on 15 minutes HICCA platform. Thank you.